Good morning. I'm Mike Griffin. I'm here to welcome you to another in a series of Aeronautics Research Mission Directorate technical seminars hosted by Lisa Porter and her Mission Directorate here at headquarters, but of course broadcast throughout NASA for those who are interested. Today's discussion will be on optimization in traffic flow management, which is one of the key aspects of the next generation air traffic management system that NASA, in concert with other agencies, is working on for the Joint Program Development Office. This is a key aspect of it because in many areas of our country, traffic flow today using today's methods is completely choked. And of course, it's in precisely those high traffic areas where we need to make improvements in order to enhance economic efficiency and in the long run, global competitiveness. Our speaker today is Dr. Banavar Sridhar, who received his bachelor's in electrical engineering degree from the Indian Institute of Science. Having gone to a graduate school with a number of students from the Indian subcontinent, I'm quite aware that the IIS is a extraordinarily prestigious institute within India. Dr. Sridhar then came to the United States and obtained a master's and doctorate in electrical engineering from the University of Connecticut. Today he's chief of the Automation Concepts branch and manages activities in the next generation air transportation technologies arena. And his research interests are in the area of modeling and optimization techniques for aerospace systems. He received the 2004 IEEE Control System Technology Award for his contributions to the development of modeling and simulation for multi-vehicle traffic networks, and led the development of traffic flow management software, the Future ATM Concepts Evaluation Tool, or FACET, which received the NASA Software of the Year Award in 2006. He's a fellow of both the IEEE and the AIAA, which I have not managed to achieve, and is an unusual accomplishment. So with that, I present Dr. Banavar Sridhar for today's discussion. Thank you. Good to have you here.
Thank you.
It's all yours.
Thanks. Good morning, and I would like to thank ARMD for inviting me to give this technical seminar. And today I would like to talk to you about the role of traffic flow management in air transportation and what are the issues and challenges facing to design traffic flow management for the future, and then talk about the research and development we are doing here in NASA in order to design this system. Could I have the first view graph, please? Okay, this is the title of my talk, Modeling and Optimization in Traffic Flow Management. Next view graph, please. Here is an outline of my talk. I will begin by giving the background for traffic flow management. Then under the objectives and payoff, I would like to talk about the research we are doing here at NASA to address some of the issues and challenges in traffic flow management. And I would cover what research we are doing in the area of models, two different types of models, aggregate models and performance models, and then talk about the kinds of optimization methods we are trying to develop to improve the effectiveness of traffic flow management, and end up with a summary of where we are. Next view graph, please. Here, what is traffic flow management? We all know what flow management means. For traffic flow management in air traffic, it is really the planning of air traffic to avoid exceeding airport and airspace capacity. And while doing that, we want to make full use of the available airspace. here I have a graphics which shows in the red background is the geographical United States, and in white you see United States for air traffic purposes, the airspace over the United States. And these are divided into centers, which are those white regions you see. And then you see some of the areas being colored red. And these are areas where traffic may be exceeding airspace capacity. In developing this, I've been using 3 times the capacity of current traffic, which is what we want to design the system. And the airspace capacity depends upon several different things. It depends upon how air traffic would be separated, and also how severe weather affects. So the capacity is dependent on many different factors, and I'll talk about them as we go along. And in order to cope up with congestion and severe weather, traffic is either rerouted or slowed down, and this causes delay. So this is a natural thing in any system where capacity is very close to demand. The system performance goes down as delay. And the cost of delay to airlines in 2005 was estimated to be $5.9 billion. This is an estimate made by the Air Transportation Association, which has all the commercial airlines as its members. Next view graph, please. So how is traffic flow management done, and what factors affect traffic flow management? When we are talking about traffic flow management, we are doing this in several different timescales. Traffic flow management could be planning traffic for the entire United States at the national level. We could be doing this at the regional level. How do we manage traffic in a given center? Or this could be at the local level. And traffic flow management involves many different people. You have pilots in aircraft making decisions about the route the aircraft takes. This could be about 15,000 aircraft if you are planning an interval for about 4 hours. And then in order to deal with congestion, there are several people in the air traffic service provider, the FAA in the United States, both at the command center and at the center. And in addition to that, you have aircraft dispatchers. These are the people before an aircraft takes off, decide how much fuel to carry, what are alternative sites for the aircraft to land, and these issues. So as I said, between the pilots, the traffic flow managers and dispatchers and the pilots, you have lots of people making decisions at several different times. And again, these people who make decisions, they also have different kinds of objectives. You have the FAA, whose primary role would be to make traffic safe, trying to regulate airspace capacity. While you have airlines which are interested in maintaining schedules, and amongst airlines we also have different types of airlines. You have passenger airlines, you have cargo airlines, and then you have general aviation. And then traffic flow not only has to deal with nominal traffic, it has to deal with various disturbances to the flow, and the major disturbances are due to severe weather, and the other kind of disturbance is equipment failure. This could be the failure of a whole airline's weight and balance system being gone, or scheduling system being down. So with all these, next view graph please. So first I want to give you an idea of how many aircrafts are flying in the United States, and to give you how air traffic looks from the viewpoint of different airlines. And what you will be seeing would be a video of traffic in the United States during a day, starting at 7 p.m. one day and ending at 7 p.m. Another day. You may be wondering why pick 7 p.m. This is a holdout from the British days where time really is in England, saying so all traffic measurements are referred to Greenwich Mean Time. So that's why this odd thing about the movie starting at 7 p.m. and ending at 7 p.m. the next day. Can I have the animation, please? So what you're seeing here is a three-dimensional view of traffic in the United States. And I have highlighted in color the traffic belonging to different airlines. Right now you're seeing American Airlines with a lot of activity at DFW. And now you're seeing United with a lot of activity in Chicago, O'Hare, and Denver. And now it is Delta Airlines with a lot of activity at Atlanta. And SkyWest, which works closely with United Airlines. And this is Northwest with a lot of hub operations in Minneapolis. And this is Southwest Airlines with a lot of point-to-point travel. And this is Just Airways, which is truly a transcontinental airline flying from coast to coast. And this is followed by US Airways. And so one of this thing gives you an idea about, the animation gives you an idea about all airlines are not equal. They fly in different parts of the United States. They have different philosophies. So in developing traffic flow management, one need to take into account how the users fly. Could I have the next view graph, please? You probably are already reading in the newspaper how traffic is being delayed, especially during this time of the year. And last year was no different. What I'm showing here is a normal day, a Tuesday last July, and another Tuesday 3 weeks later, where we had severe thunderstorm activity. On both days, we had approximately same number of flights in the order of 54 to 56,000 aircraft. And on the normal Tuesday, the delay was felt 42,000 minutes. This is the aggregate delay felt by all the airlines. In air traffic, we don't count aircraft which are delayed by less than 15 minutes as a delayed aircraft. Anything which is delayed more than 15 minutes is considered as a delay, and that's what goes into the aggregate delay. So here I am showing in blue color all those flights which are delayed by less than 2 hours. And in red color, I am showing all those flights which are delayed by greater than 2 hours. And the big thing to notice is between a normal day and a severe weather day, the number of flights which are delayed by more than 2 hours almost triple. And could I have the animation, please? So here I'm just showing traffic. This is just like the 24-hour movie. You see all the weather is indicated by the green blotches you see, and severe weather is indicated by yellow or red yellow or red areas. And the traffic tries to move around the weather, and this is what causes delay. And you can see Some of you see the traffic go up and down because we are going from the nighttime of the first day to the daytime of the second day. And you see traffic skirting bad weather, and this is what causes delays. I'll let you, the movie is more descriptive than what I can add to it, and I'll let it run for 30 seconds. And you can see all the areas of intense activity in the East Coast. You can see aircraft coming from overseas which are delayed in this. And can I have the next view graph, please? Okay, how do we manage the traffic flow today? And I have two pictures. On the left-hand side, you see the continental United States, and the red square indicates weather near Chicago. And when this happens, we have a lot of alternate routes already pre-planned. And these are called as severe weather routes. In this case, what we do is we take all the flights originating from the West Coast and take them to points in Sacramento, Helena in Montana, and Bryce, and then bring all these aircraft up north of the Chicago in the Minneapolis center. And then once we are past the weather, we take them back to the appropriate airports on the East Coast to LaGuardia or JFK or to Dallas. Now, as you can expect, when we move all the aircraft north of Chicago, the Minneapolis center, which is shown in black on the right-hand side, is going to feel the burden of a lot of extra traffic and causing congestion. And another way we try to control traffic in periods of severe weather would be by holding aircraft at the departure airports. And this is called as the ground delay program. And I mentioned that when you move all the aircraft to the north of Chicago, it's going to cause congestion. The way we deal with congestion today is by slowing down the aircraft. That's by trying to space the aircraft greater and increasing the space between the aircraft bigger and bigger, and it's called as miles in trail. And if severe weather routes do not work, ground delay program does not work, and miles in trail, then we take the last minute action of doing local rerouting. Could I have the next view graph, please? So here, what I'm trying to show is in the square blocks I have with the green and yellow color, or how the congestion in the two sectors in Minneapolis center are faring. I would like to see them all green, which means that I would like to keep the capacity of the sectors there below safe region. And so in Minneapolis center, as it is in the normal situation, I might have congestion. And because of the weather, we impose playback and ground delay programs. And this causes even more congestion, which may be one option. Option B in the bottom half of the view graph is to take local reroute. That doesn't seem to solve the problem. So we may follow the playbook and the GDP by a miles in trail followed by a local reroute to completely solve this problem. So we have several sort of ad hoc ways to solve the problem. So the result of this is the same aircraft may be feeling the same multiple effects which might make it more delayed. Could I have the next view graph, please? So this here, I want to sort of summarize what are the issues facing the current traffic flow management. One is there is insufficient information sharing between the various decision makers. What I mean by this is sometimes airlines make schedule changes as well as cancellations. The service provider, the FAA in this case, he is not aware of it. And sometimes the airlines also have the exact information about what is the weight of the aircraft, which is very essential in making predictions which are central to traffic flow management. So we don't have the correct information. And the other times, the FAA knows about where the congestion is going to take place. And all this information is not always transferred to the right parties to make the correct decisions. And like I mentioned in my example, there is decisions being made at the national level, regional level, local level. These are not always coordinated. And this might make some aircraft pay double or triple penalty. And the other thing is, in today's system, there is not a lot of coordination between what the airlines want to do and the level of collaboration really mostly happens at the national level. There are, in the severe weather telecoms, both the airlines and the FAA participate, and we would like to increase that, not only that level of collaboration, but collaborations even for shorter durations. And lastly, there is, in spite of all the automation, there is still the amount of automation is very limited. And because of that, the number of options one can try becomes limited. Next view graph, please. So what are the challenges facing the design of the future TFM? And there are various forecasts of how traffic is going to increase in the future. So, what we are trying to do is design for 3 times current traffic. This would enable us to meet irrespective of what forecast turns out to be true. And also we want to design for new type of vehicles. And also in the future, maybe we will have more unscheduled flights. This is to sort of meet on-demand air traffic service. And also the future TFM, we want to take into account collaborative decision making much more than what is possible today. So we want to increase the airlines' participation in decision making, both in the strategic traffic flow management as well as tactical flow management. And one of the today, as you saw, weather is a major uncertainty. Today, in all our decision-making, weather is considered to be deterministic. And we would like to see how this can be addressed using probabilistic information. What is appropriate probabilistic information? And since we depend a lot, we are going to depend a lot on automation as solving many of these problems. We need to look into automation which degrades gracefully, and particularly how does automation behave under off-nominal conditions. Next view graph, please. So, so far all I did was to talk about what are the problems with the traffic flow management. Now I would like to talk about what are the types of research we are doing here at NASA as part of the airspace systems program to address some of these issues. Next view graph, please. Here, what I have tried to show is I'm a control systems engineer, so everything looks like a block diagram to me. So here at the top, you have the air traffic system. What drives the air traffic system is user schedules and flight planning. And based upon the nominal schedule, you have a certain system performance. And the the control system or the air traffic system gets perturbed because of bad weather. And we have observations of traffic. And we also have models of traffic flow and also models of the weather. Based upon the traffic flow, we can make traffic predictions. And based upon the traffic predictions as well as the observed traffic, we can say, well, we need to change the current schedules, or these are the traffic flow management initiatives, as we call them, taking also into account the views of the airlines in such a way to manage the system. So this is done by in the optimization part by trying several different initiatives or traffic flow management policies to come up with the best policy. And the best policy is then fed back to the actual system, as you see in the flow diagram. So in other words, we would like to investigate modeling, simulation, and optimization techniques to minimize total system delay or some other performance function. And the constraints to the problem are the airspace and airport capacity, while accommodating 3 times traffic and taking into account weather uncertainty. Next view graph, please. Okay, next I would like to talk about 2 different kind of models. The first model is the aggregate models, and that would be followed by a discussion of what are delay models. Next view graph, please. Here, on the left-hand side, you saw those, in the animation, you saw a lot of aircraft. And so the Lagrangian models are the standard models for the aircraft which you study in flight mechanics. These are where the aircraft is modeled in terms of its X, Y, and Z positions, maybe the altitude rate and the speed. So if you take 6 states for each aircraft, and for 15,000 aircraft, you're really dealing with a dynamic system with 90,000 states. So one of the things we looked at in our Eulerian models is, can we, for traffic flow management, especially for traffic flow management for strategic purposes, is it possible to aggregate this large system by an equivalent, simpler system, but at least which captures the essence of the traffic flow? And one of the models we looked at was, can we approximate this by a model where the states of the system are how many aircrafts are there in a given region. And we looked at the centers as the one natural set of states. So I will be talking about approximating the air traffic by 23 states. The reason for the 23 is there are 20 centers and in the continental United States, plus Alaska and Hawaii, and all the international traffic is combined into a 3rd state. So that's how I ended up with 23 states. Can we have the next view graph, please? Okay. The figure looks complicated, but it is not. Here, I am looking xi at k is how many aircraft are there in region I at the current time. And then we want to know how many would be there an instant of time greater. So the way the number of aircraft in a region changes is because there are new departures originating from from airports in that region. Then also the number of aircraft decrease by the number of arrivals at airports in that center. Then there is also flow of aircraft from the region I to its neighbors. It's adjacent. And also, in addition to that, there is the inflow from the neighboring centers to the region. So if you put it all and based on the conservation of aircraft, you get an equation which relates xik plus 1, that is how many aircrafts are in this region at time k plus 1 based upon how many were there at the previous instance of time. And I have these betas there. These are the fractions which go from one region to the other. And these are determined based upon historical data. And when we do that, I can take all these equations for all the centers and put them as a nice a discrete time variant equation which says xk plus 1 is equal to a matrix AK, a system matrix AK, multiplying the states plus dk, which is a vector of departures from the various airports in different centers. And some of the questions one would think here would be, at the center level, what is an appropriate interval of time? We have found that using 15 departure rates of 15 minutes are adequate to capture the flow. And also the A matrix, we have tried them. It's time varying, but it doesn't vary every 15 minutes. We have tried making it vary every hour or every 4 hours. So let me go to the next view graph to show you how the A matrix looks like. The A matrix is what I call quasi-diagonal. Here I have arranged the A matrix so my states are grouped into the centers on the West Coast, followed by the centers moving towards east, followed by centers in the Midwest and the East Coast. And one of the things you can notice, and should be obvious, is that the dynamics of the center counts on the western states does not change immediately to changes happening on the East Coast. So there is a natural time scale to the problem. Next view graph, please. So we have shown a linear dynamic traffic flow system model with a slowly varying A matrix, and a Gaussian departure representation is adequate to represent a traffic flow at the center level. One of the advantages of this kind of a system is that we have been able to reduce the model order significantly. And the other big advantage is there are plenty of well-known techniques in modern system theory, which can be used for estimation, can be used for control, and many of these things are readily available to be tried out on these systems. So currently we are exploring how the tools and techniques of systems theory, all the various tools you can get in a program like MATLAB could be used to design the traffic flow at the national level. Next view graph, please. Now let me switch gears here from traffic flow models to delay models. One of the first things I noticed when I started working on this was we collect a lot of data about traffic, we collect a lot of data about weather, and we also make a lot of observations about delay. We make observations about different kinds of delays, center delays, aggregate delays at the national level. And so the idea was, can you look at all this data and can you build a model which the relation between weather, traffic, and delay is very complicated. We don't know the physics of it, but by looking at all the data available, can we build models for delay and other system performance indices. So there are several advantages to doing this. First of all, this helps you understand how current system works, how delay in the current system is dependent on weather and traffic. And it may also help you to calibrate your performance for tomorrow. To see how well the various actions you're taking is influencing the performance of the system. On the left-hand side, you see traffic in the United States at a particular instant of time. And and that is represented by the matrix T of K. So each element in the T matrix represents how many aircraft are there in that element at time K. On the right-hand side, I am showing where the weather is at that time. So, and you can look at the absence, or I'm representing the weather matrix as either an element 1 or 0. It is 1 where there is weather at that time and 0 otherwise. And I have defined at the bottom a complicated looking function which simply says it is called WITI, or Weather Impacted Traffic Index, which is really asking how many aircraft are affected by the weather at this particular time, which you can get by sort of multiplying, making an element by element multiplication of the two matrices. And that's what the equation at the bottom says. Could I have the next view graph, please? So if you go and compute WITI using weather and traffic data, you get a curve which I have shown on the right-hand side. And it is a curve which at any instant of time shows how many aircrafts are affected by the weather. And it has the same natural rhythm as the ebb and flow of traffic during the day. And only thing, the traffic is being modified by the presence or absence of weather in different places. And what we want to do is take this WITI, and we want to represent the WITI by its features. What the features can be. The features could be the mean value of WITI. It could be the variance of WITI, or it could be how can I represent the time variation, how can I represent the amplitude variations. So on any given day, you can compute what these WITI features are. Corresponding to the same day, you have what is the total aggregated delay observations from the FAA. So if you have this data for a large number of days, you can fit a regression model relating delay to WITI features. Once you have this weight W, then for another day, P for example, you can, if you have the predicted traffic and the predicted weather, you can go and compute the predicted WITI features, and multiplying the WITI features with the weights which we have determined based upon historical data and linear regression techniques, you can estimate the day for day P. Now, we did this using linear regression, and one of the things which is characteristic of all queuing systems is, as the system capacity gets very close to demand, the delays increase. So we thought maybe we can improve the delay estimates instead of fitting one linear regression equation to perhaps multiple ones. Could I have the next view graph, please? And that's what I'm trying to show here, a piecewise linear WITI model. So we get, as you go from the left to right, you are looking at a day in the future. Based upon the predicted weather and traffic, we can compute a WITI at the national level, as I indicated. And that was the single linear regression model. At the same time, if I sort of group tomorrow's delay into 3 different areas, low, medium, and high, for my computation, I'm considering any day which has less than 50,000 minutes of aggregate delay as a low delay day. Moderate or medium, anywhere from 50,000 minutes to 100,000 minutes. And anything above 100,000 minutes, I'm considering it as a high delay day. And if I can group my day as to falling into one of these 3 categories, instead of fitting a single linear regression equation or model, I can fit 3 different linear regression. And that's what we plan to do. And then you had a question, who is going to tell you whether tomorrow is going to be a low delay day or a medium delay day or a high delay day. And this we are going to do by a classification scheme, which is based upon how the VT behaves at the center. So far, we were only looking for VT at the national level. By going one step below and looking at how the various centers of VT are behaving, we have been able to come up with a classification scheme. Next view graph, please. This one just shows you the behavior of the center level VTs. Along the x-axis is the time, along the y-axis is the various, I'm showing you the 20 different centers and how the average VT in these centers behave as a function of time. Could I have the next view graph, please? Now here, we have used this kind of model. We have developed the piecewise linear models. We have tested them using weather, traffic, and delay data for the years 2004, 2005, and 2006. We are collecting all this data for 2007 and would again do our validation with the 2007 data also. And this is how I'm trying to show you here the comparison of how the three-region VT model works. On the x-axis, you have the predicted delay, and on the y-axis, you have the observed delay. And here I am showing the data for the year 2004, and you can see, I'll come in a minute, how it performs. And you can see that there were not all the observations and the predictions match exactly. And that is to be expected in a complicated system. And if we use the single linear model, we got a correlation coefficient of 0.54 with a standard deviation of 48,000 minutes. Now, if somebody were to tell you exactly what kind of delay tomorrow is, that is, if you had perfect classification into low, medium, and high, we were able to bring the standard deviation from 48,000 to 18,000, 16,000, and 37,000 with perfect classification. But with the classification we have, we are able to bring down the correlation coefficient from single to three-piece linear from 0.54 to 0.8, and correspondingly the standard deviation goes down from 48,000 minutes to 27, 20,000, and 38,000. The high end is always going to be a problem in fitting the model because there are not, fortunately, there are not too many really large delay days. Okay, and so this is where we are with reference to our VT modeling. We hope to improve this in even more because the weather information today not only has where the weather is severe, but it also has where the echo tops are. This is, above which, the level above which there is no weather. So we want to use that as an additional input to our VT model to improve it even further. So next, can I have the next view graph, please? Now, so far I have talked mostly on models, both aggregate models and delay models. Now I would like to move to the optimization methods. Next view graph, please. In any optimization problem, to formulate it, you need to have the systems dynamics. My systems dynamics is expressed as a standard state space equation. And the state here, like I mentioned earlier, could be specified in two different ways. I could either have the either the Lagrangian state or the Eulerian, and also the size, of course, depends on the planning interval. And my control variables are for this problem are generally departure time and the route followed by each aircraft, or the rates of departure in the strategic model. And the cost function could be one of several things. It could be you want to minimize the variation from the schedule, or you want to minimize the delay from the variation. And you may want to include factors like we want to minimize fuel. Maybe we want to bring in equity considerations and a number of other things. And the constraints are basically we don't want to exceed either the airspace capacity or the airport capacity. And these constraints could be very large in number. And we also want to take into account weather uncertainty. And the standard formulation on this one is, it's a real two-point boundary value problem. You have dynamic equations, you have endpoints, and state constraints. So you can go ahead and formulate it as a standard two-point boundary value problem. How does one solve these problems? Next view graph, please. So I talked about the dynamics. I don't expect you to read all those equations. The cost function, you take expectations over the uncertainties, and the number of stages in the cost function really depends upon the length of the planning interval and the size of the time interval itself. And dynamic programming is a standard approach to formulating the solution to a lot of these problems. And solving the dynamic programming, you really will get the control policy. But dynamic programming has always had the problem of the number of dimensions grow too large, too quick, and one has to resort to some kind of an approximation. So the dynamic programming here is used just to provide you with a framework so that the approximations you make are consistent. Okay. So could I have the next view graph, please? So what we are looking for is to develop heuristic methods, linear methods, nonlinear methods. We want to decompose the problems in the most appropriate way for our problem. And so we also want our methods to accommodate user preferences. We want to be able to pursue multiple objectives. We want to see how the traffic flow solutions made up of 40 controls, how are they over quite a long durations of time. And also we want to make sure that the solutions that we compute are stable. So how does one measure the success of TFM optimization methods? The graphics on the right-hand side, I have the cost function along the y-axis and the space of all solutions along the x-axis. Or this is generally x-axis or many different axes, the axis of solution space. And now a good measure of how well the TFM optimization is working is really to look at for a baseline scenario, what is the expected delay today? And how much can you reduce it by, let us say, by trying to try several options by a what-if kind of methodology. And then if one can really compute dynamic programming, that would be neat. Or some approximations to the dynamic programming, some approximation. So your value the TFM optimization is adding is to bring how much have you brought down from the baseline to the approximation. Next view graph, please. I just want to take a minute to give you a comparison of the optimization we are doing in traffic flow management with some other areas where optimization is used. One is a railway network. Here you're really trying to assign 5,000 trains to 390 stations. Has 56,000 variables and 32,000 constraints. The other is the power generation problem. Here you're trying to generate hydroelectric and thermal power by using 100 generators and 250 reservoirs. This problem has about like 120,000 variables and 25,000 constraints. And the one which is most talked about, but very hard to find actual information, is scheduling of information networks. You have millions of end users, maybe 100,000 routers, 10,000 autonomous systems. These are used in various applications, web, peer-to-peer networks. And then we have, I want to contrast that with one subset of the traffic flow management, which is the Chicago arrival flow management, has 29,000 variables, 32,000 constraints. And this was an assignment which was given to me when I said, we are working on TFM optimization. So it has been very hard to find examples which really provide you a comparison. So let me go to the next view graph. Here, I want to describe a traffic flow management, the Chicago arrival flow management, to provide you how we are following the traffic flow management optimization. Chicago is always congested. And here I am showing the flows to the Chicago airport through two fixes, Pullman and Knox, for flights coming from the East Coast. You see the various streams of traffic, one coming from the New York airports, Boston and Cleveland centers, the international flights, all coming to Chicago over Pullman. And at the bottom, you see coming over Knox are all the Philadelphia and flights from other airports in that region. And you also see all the flights coming from the Washington area airports and the Indianapolis center. And at the bottom, you see all the flights coming from the south. These are flights coming from Jacksonville and Miami centers. Now, how do we manage this flight today? Next view graph, please. So the standard operations today is when there is congestion in Chicago, you try to slow down the planes coming to Chicago area. So which means that you slow down, you have the two upper streams feeding Pullman. I'm kidding. Would be slowed down from 10 to 20. So in order to achieve 10 miles in trails, if you're getting feed from two streams, you have to make them 20 miles in trail. Similarly, the lower Knox fix has 10 miles in trails and has three feeder streams, which have to be made to be even more separate with a 30 miles in trails. And now let me give you what this and how much delay this results in. Next view graph, please. Before I do that, here is how we are going to model that. We are going to model that as a problem of constraints in the optimization. On the left-hand side, you see all the constraints which are because of the airport, the departure airport capacity constraint, the arrival fixed constraints, and also the Chicago arrival capacity constraint. And on the right-hand side, you also see in green the various sectors over this problem takes place, and all of those sectors have their own high-altitude sector capacity. So for this problem, if you formulate it as a TFM optimization problem, for a 3-hour period, you have 29,000 variables and about 32,000 constraints, and we are looking at 99 flights at 51 airports and 201 sectors. Next view graph, please. So if you solve this problem, the baseline method today gives you a delay of 785 minutes. There no decision support is available. We could improve a little bit by using a what-if methodology by sort of a ration by schedule or first come, first serve. which reduces the delay to 735 minutes. As opposed to this, we have an optimal solution using integer programming, which reduces the delay from 785 minutes to 343 minutes. Can I go to the next view graph, please? Now here I am trying to give you an idea of what optimization can do. Here I have traffic demand, en route capacity, and Chicago arrival capacity. I call them 1x if it is what it is today. So we saw that for under today's condition, the optimization results in 343 minutes of delay or 4 minutes delay. So since we have the simulation and the optimization going, we tried several different scenarios. First was we want to design for 3x. What happens for 3 times today's traffic? The optimization was not able to find a solution. By that, what I mean was the delays got to be so large to maintain the constraint. We said this is not a good solution. And then so we tried various alternatives. As part of the NASA research program, we are also trying to enhance the en route capacity as well as the arrival capacity. If the capacity were to be increased by 2 times what is today, so those are the 2x and 1x you see, increasing the en route capacity by 2 times, keeping the arrival capacity same, gives you 18,000 minutes of delay, still not very desirable. So we tried various alternatives when we increased the en route capacity to 3 times and the Chicago arrival capacity to 3 times. For this case, you get back your 4 minutes of average delay. But this one, you have to, the optimization here is only looking at departure controls. We have not tried to optimize on the routing strategy. We are keeping the same routing strategy, but just controlling departures. So a lot more can be done here to improve the amount of delay. Could I have the next view graph, please? I mentioned weather several times, but I didn't tell what we are doing to address this. There are various different kinds of weather, and almost 75% of the traffic delays today are attributed to weather. And weather reduces both airport and airspace capacity. And the biggest challenge for addressing weather in TFM, so far weather has always been used as for display purposes as well as interpretation by the human person doing the control. So our challenge is to translate weather into computational use, which means we have to be able to say, because of this weather, the airspace capacity is going to go down by this amount. And similarly, predicting weather is hard, and we have to decide what is an appropriate prediction of weather other than deterministic. Is it going to be described as a distribution, or are we going to have several scenarios of weather with some probability attached to it? Could I have the next view graph, please? So we are assuming that we will get a lot of help from the meteorologists and other weather aviation people to help us here. And when the weather is available, either as probabilistic functions or as scenarios, the idea is to, I don't know whether you can see the graphics very well, but what I'm showing at the bottom there is that because of the weather, the arrival capacity in an airport goes down from 60, the normal one, to 30 under bad weather. And the weather may lift at 8 o'clock or 8:30 or 9 o'clock with various probabilities. So given that scenario, we can design a optimum policy taking weather into account. Can I have the next view graph, please? Now, I talked about optimization at the national scale. And the example I showed you was for Chicago. Now, how does one put together all the small pieces together to form the overall national picture? Here, I have tried to illustrate that by looking at the Chicago Center and the New York Center. And you can solve the problem for the Chicago Center assuming the interaction from the New York Center to it is constant. And once you get that solution, you can go to the New York Center and assume that the input from the Chicago Center or the influence of the Chicago Center on the New York Center is a constant. So by doing this successively, and this would be the role for a coordinator or some kind of a mechanism which puts all these solutions together. And I like to illustrate that with a diagram. Can I have the next one, please? So here, this is called optimization by successive approximation. These things go by several different names depending upon which discipline it is, whether it is operations research, control systems. Sometimes this is also referred to as Lagrangian approximations or Lagrangian multipliers approach. So it's very simple. It's like how does one do gradient optimization. So when you're solving the problem for the Chicago region, you hold the effect of the New York region constant and you move along the gradient and you get a local minimum. And at that point, you hold the influence of Chicago region constant and optimize on the New York region. So by successive optimization, you get to the minimum. This, of course, assumes that you are closer to your optimum solution and your problem doesn't have multiple minimums, which can be addressed in several different ways by starting from different starting points or by other techniques. Could I have the next view graph, please? Everything in traffic flow management and all this involves lots of data. And and so we are really dependent on some kind of a software environment to solve the problems. Here at NASA, to solve the traffic flow management and dynamic airspace concepts, we make use of our tool Facet. And one of the neat things about Facet is that it's available to all the universities all over the world. And also it's available to all the US companies. As I mentioned earlier, Facet is a simulation environment. So we have been spending a lot of time trying to integrate Facet with the other optimization methods. So far, we have been able to integrate it with MATLAB, which means a whole lot of techniques is available to try to come up with new methods. And also, MATLAB is a tool which is used extensively by the non-air traffic management community. So we get all that development as tools for us. And we have also integrated with the linear programming world. Cplex is the software, the sort of the Cadillac of integer programming software. And they charge those kinds of prices too. And we have a lot of different elements in air traffic management in the airspace program. And so in order to integrate this, we are trying to make Facet talk to all these other tools. Center Tracon automation system is our premier environment for doing all our separation assurance calculations. So we have integrated Facet with CTAS. What this does is, when I was trying to show you the examples of optimization, I was trying to say 1x, 2x, 3x. We don't need to do 1x, 2x, 3x. What we can do with this environment is really have the new separation assurance algorithms work in the CTAS environment combine the facet and the optimization environment together, and you can really evaluate what we are getting in the program in an integrated way. It's not like delay being reduced artificially, assuming I'm going to get so much from separation assurance. That's where it helps us to the integration. And we want to integrate all these in our ACES. ACES stands for Airport Concept Evaluation System. And that is our sort of gate-to-gate simulation. That would have, that program would interact or would have simulations of all the other features of the air traffic system. So we will be able to integrate how effective the tools we have developed are in a real environment. Next view graph, please. And we are trying to do, we are trying to do all this through the development of what they call as APIs, or application program interface. So which simply means facet talks to the application program interface, which in turn talks to the optimization environment or the CPLEX environment, or maybe to CTAS. And this has proved very, very effective. And one of the advantages of this is, as part of the program, we have a lot of NRAs. And so there is a lot of development and research work which is being done in addition to what is being done inside NASA. And this would help us bring all that research and be able to evaluate them in a sort of a natural environment. Next view graph, please. And I think with that, I would like to go to summarize what I have talked so far. Could I have the next view graph, please? So I try to give you an idea of what is traffic flow management, what is the role it plays in air traffic management or in air transportation, and how does one go and design that for the future, assuming, so we use the design variable of 3 times. And why is it so hard? We've been talking about traffic flow management. People have talked about optimization for large systems for a long time. It's really, there are several factors. One is we have a large number of aircraft. I kept saying 15,000 there. I'm only taking into account the number of aircraft which filed plans, and only about 4 hours. But if you took all the aircraft, the GA and other aircraft, it would triple. So there is, we have to contend with uncertainty in weather prediction, and people have different reasons to make traffic flow management solutions. And I hope I have conveyed to you that how TFM modeling and optimization methods provide a methodology to make effective flow decisions to reduce to improve the performance of the systems. Thank you.
Hello, I'm J.D. Harrington. I'm going to host the question and answer portion of today's presentation. Before we get started, a quick caveat. Before you ask a question, if you would wait until we get the microphone to you and then identify yourself before you start. Also, a reminder to our centers, you are eligible and capable of taking questions from you as well. So if you would, by all means, step up, and we'll be ready to do that as well. From headquarters here, do we have any questions? All right, I have a couple that were emailed to me this morning to get us started here. So, Doctor, it can't really be argued that safety incidents are a rare occurrence in today's society, and that in the national airspace. In this context, what is meant by maintaining the safety of our airspace? How do you maintain and how do you measure that?
Okay. The safety in the air traffic system is done at many different levels. You have all, and that's the beauty of why we are able to maintain such high levels of safety. It's done at the traffic flow management level, which I talked about. Safety for me just means taking planning actions which don't develop into a bad situation. That is, I'm really trying to keep the airspace capacity at a limit where in today's system the controllers can manage that aircraft very effectively. That's just a limit on how many aircraft should be in a given area. But taking your question one step further, safety also is dealt at the next level by trying to maintain separation from the aircraft. That is, you have 5 miles in the horizontal directions and 1,000 miles vertically. And this is what is done in the separation assurance. And on top of that, you have if for some chance the controllers fail, then you also have the traffic collision avoidance system in the system. It's all these levels which go into building safety. And measuring safety is really hard. And a lot of experts other than me are really working on trying to do this. And trying to ensure safety in an automated system is even harder. There are lots of programs trying to understand how do you study safety in the presence of automation. So I can elaborate if needed.
Okay. We do have a question from Langley.
Hi, Bonivar. This is Richard Barheit. I want to thank you for your excellent presentation. You talk quite a bit about the impact of weather information on predictions, on delay predictions and optimization, and wondering if you might comment on your thoughts of the impact of trajectory information, either the level of trajectory information or trajectory uncertainty on either predictions of traffic delay or your optimization. Of course, as you know, with the move towards trajectory-based operations and JPDO, that this will probably be a big factor. Thank you.
Thank you, Richard. The impact of trajectory predictions, the most critical element really comes in knowing what the intent of the aircraft is. It's really it's not so much the accuracy of the current position, which of course is very accurate based upon the current navigation system. It's really knowing what the aircraft is going to do in the next hour or two, and knowing it precisely is what makes traffic predictions hard.
Any other questions here at headquarters? Okay, one more here that I had prepared. How do you validate system safety when you have a highly automated, non-deterministic, complex system, really, with several uncertainties in that?
Okay, this would be the hardest challenge, not just for me, but for we as a nation. Conventionally, the way we have built safe systems is to make them redundant. Like the classic example is the landing gear system. In the landing gear system, you had the landing gear which could be operated hydraulically, which was the desirable mode. If the hydraulic system failed, we had electric motors. If the electric motors failed, we really had the guy who could go and crank the landing gear down. But the neat thing about these systems were one thing did not interfere with the other system. But this is very hard to do in the current automated world, because it could be the ultimate safety depends upon not just one thing. It is the safety of the components which go into the system. It is the safety of the software and safety of the software for critical systems. Really, really big challenge because you may have designed your software to be perfect, but this software may be sharing a bus with another software, and you don't know whether the operating system works in such a way that somehow one overwrites the other. So it's a major challenge, not only for just our program. It is a challenge for many, many other automation systems which we are working on. And the Department of Defense really has a huge program, several orders of magnitude bigger than our program, looking into these kinds of problems.
Okay. I believe we have one more question from Langley as well. Langley, go ahead.
Hello. My name is Bernell McKissick, and I have two questions. One is, what research is needed to improve the predictions of, say, faucets? And two, how do you validate faucets since it has predictions? I mean, how do you validate something like faucets?
Could you repeat the question, please?
Both questions?
Yes, please.
The first question was, what research is needed to improve faucets?
Oh, okay.
What technical research can you do to actually make the program better? And the second question, how do you measure the validity of something like faucet? How do you validate it, if it's possible to validate such a program?
Okay. We have spent a lot of time trying to, facet is just a simple prediction of air traffic. So the way to improve air traffic predictions of in any software, whether it is facet or any other software, would be to make sure that your aircraft models are right. And I think they are as good as they need to be for the purpose for which it is developed. Like I mentioned in response to the earlier question, you can improve predictions of facet simply by giving facet the correct information. The problem is not with the model. The problem is with the kind of information you get. What happens is facet is what I would call as an open loop model, but there are a lot of feedbacks, and it assumes those feedback is constant within the prediction interval. That is, what I mean by that is, if you are predicting how traffic is going to evolve over the next 4 hours, it's sort of assuming that the aircraft would depart at a certain time. But if that information changes between now to the next 4 hours, the predictions are going to be different so to the extent you can get those predictions correct, and to the extent that between now and the next 4 hours, a lot of people don't change their mind, and the software really cannot do anything about it. You're really looking at a linear time varying system with feedback which is changing, as long as we don't know what the reaction of the various people, the airlines and the other traffic flow management. The predictions they're not wrong, they're different, because your assumptions changed in between. The only way to improve the modeling capabilities are correct, but if conditions change, unless we know what the changes are, you can't tell it. Other than you can do sort of stochastic versions of it, but that's only going to be as good as your knowledge of the distribution functions are.
All right. Are there any further questions here at headquarters? All right. We have one up here in the corner here. Stand by.
Yuri Gaudiak. I was curious if you've looked at the impact of very light jets. They're about to be poised to make a big impact into the national airspace, and how would they affect the current system, and especially in terms of their dynamic scheduling and probably higher sensitivity to weather?
Okay. I have not done it, but there are a lot of people at the FAA who have looked at what is the impact of very light jets on the system. And, these are all, it also depends upon how many of these aircraft we are going to have. What would be the business philosophy for these? It depends upon, there is a recent article which sort of looks at how much, whether it is a light jet or whether it is a commercial transport, the services needed to for these is the same. So people are talking about, is there, so how many light jets are going to be there is not clear. And, in very congested areas, maybe you have to adopt a different kind of business models to be able to accommodate them. And there are quite a few people who have looked into the impact of very light jets on the air traffic, and I will be happy to send you the references.
All right, any other questions? All right, with no other questions, we'll conclude today's ceremony, procedure or presentation and that. I'd like to thank Dr. Bhanavar Sidjar for his time here today. And if you'd like more information about this program or any other aeronautics program, please visit us on the web at www.aeronautics.nasa.gov. Thank you.